All right, I'm going to try talking about the Stieltjes integral. Most people talk about it by saying, let's say we have a function um, f of x d g of x. Then if g of x is continuous, then they can say that it's sort of like doing the integral of f of x g dash x dx. But then if it's not continuous, then you have a different way of looking at it, which would be, say, I'm trying to remember how it was. It was oh, forget it. If go look at other videos and you'll see the technical definition of how to do it. But if you look at something like this, let's say you've got a function g of x, which equals, let's say, 0 for 0 less equal to x less than 1, and then it equals 1 for 1 less equal to x less equal to 2, let's just say. Forgive me, I'm just doing this on the fly, so if you pick up little mistakes, please put it in the comments. All good. Now, if we have that case, then we have a function that sort of looks like this for g of x. So let's say we've got x here and g of x, and we end up getting that function. And this is at x equals 1. We have that jump. So basically, there's no change in the function except at this point, x equals 1. You couldn't do a Riemann integral on this. So there are ways that people have shown how to do it. Long story short, it would be f of 1 times 1. That's convolution, I mean times. F of 1 times 1, because the change happens at x equals 1, which is what we've got there, and the change amount is 1, right? Now, so far I haven't told you anything you wouldn't have known by looking at other videos. Where I found it helped for me was to come up with thinking of it more like this. Let's say we have our plane f of x and x, but what we do is actually create a 3D plane. Let's see if this works. All right, that sort of works. Made a little stuff up. All right, and we say that this is g dash x. So what we end up getting is a volume. This is more of a geometric way of understanding it. I've only looked at this for a short period of time, so this will cover a situation where we have a jump discontinuity. If it becomes a bit more abstract, it may not work, but this definitely helped me to understand what's really going on, at least at this level. So if we have that g of x in this particular case, let's look at an easy example first, right? So an easy example would be, let's say g of x equals 2x, so that g dash x equals 2 dx, okay? So therefore, in that particular case, we could say that, let's say f of x equals x, right? So then the integral of f of x dgx in this particular case would equal the integral of x multiplied by 2 dx, right? Which is just the integral of 2x dx, which is x squared, right? Plus some constant. Forget that for a moment. So how does that look in the 3D version? Well, the 3D version is this: g of x equals 2. So let's just say that's 1, that's 2. So g of x is here. That was a bad line, wasn't it? Let's try using this. There we go. So at this point, we've got g of x equals 2. Okay. Sorry, g dash x, sorry, equals 2. So the derivative is 2, okay, because the function was 2x. Now, we know that x, f of x equals x, is just a line, right? Let's just make it, I should change the color, make it a bit easier to see. Let's just put it in green and go this way, right? So let's just say that f of x equals x, okay, along this line. So what would the area under the curve be normally, right? The area under the curve would normally be, let me continue, no, let's try using red, and we'll go down this way, right? And the area, as you can see, would be this component, okay, which happens to equal x squared over 2. Okay, that would be the normal integral there. Now, what we're doing is extending it out this way. So what we get, whoops, that is not right. Let me reverse that. What we get is that, and that. Okay, so now we have x squared on 2 times 2, which gives you x squared. So we have a volume, because the volume is this area times the length, okay, which gives us x squared. Now, if you notice, that was actually our answer, okay? So the volume is x squared because we've got the original plane multiplied by 2. So what happens in the case where g of x is discontinuous? Okay, if it's discontinuous, let's just go back to our other example. So I'll redraw this, okay? And here is f of x and x, and our gx plane, we'll draw out here, g dash x plane, I keep saying g of x, so g dash x, okay? And if we had the function where g of x equals 0 for 0 less equal to x less than 1 and equals 1 for 1 less equal to x less than 2, then the only change happens at 1 because it's flat otherwise. And you can see it here. If we go across, it's 0. And then up here at x equals 1, we get a jump. Okay, and then it remains at the value 1. Okay, so there's our jump. So what's actually going on? It means that the function is 0 at this point. So if we go back to doing our function f of x equals x, what happens this time? Well, this time, if we look at it, right, you'll notice that our volume, okay, let me go back here. Our volume is, we've got this flat surface multiplied by 0 here, and then right at this slice, this 2D slice, which is where f of x equals 1, right, we've got that length of 1. So our 3D volume collapses into a 2D slice. And here it is, our 2D slice. That 2D slice is an area of 1. So it turns out that the integral, okay, when we're using this function, a discontinuous function, is just 1, which happens to equal, of course, f of 1 times 1, which is how, if you look at other videos, that's how they'll end up calculating it, right? But basically what's going on is that the distance along the g-x component is 0 here. So you only get a slice out of the original volume. And that, to me, makes a lot more intuitive sense on what that integral is actually doing. I thought I'd share that. Let me know your thoughts. I've just done this off the fly, so I'm sure that there are things upon which you can expand or say, no, I would have done it this way or that way. But it's just to help push along the thought process so that you can get more of a geometric understanding, the way I see it as a geometric understanding of Stieltjes integral. Ciao!